Hello and welcome to the first session in the Hitchhiker's Guide to Artificial Intelligence. This is a series that will be going on for the next 6 days at the same time. It's a little confusing in terms of the date because it is now the 13th of June in China and Asia as a whole. It's still the 12th of June where I am here in California, but it'll be going for the next 6 days. And this is really intended as an introduction to what I think is going to be a real game changer in the world of architecture. If we can talk of two game changers in the world today, I'd say that COVID and AI are the two ones. Let me first of all give you a glimpse of the potential of what I'm talking about. This is some work from Daniel Bolojan, to my mind, far and away the world leader in terms of the application to AI in architecture. This is a study that he did of the Sagrada Familia by Antonio Gaudi. And it's part of a work that he's ongoing work. This is the very latest version of this that he showed in the Venice Biennale just a week ago. Daniel will be talking about this in 2 days' time, and it is absolutely astonishing work. So the idea of this series then is to try and lay out for you why we need to take AI seriously, to try and look at the possibilities it can afford, and to go through in a very seemingly introductory way the different possibilities that we can find in AI. My name is Neil Leach. I'm a theorist. I'm one of the co-founders of Digital Futures, along with Philip Yuan, 11 years ago now. And I'm teaching at FIU, at Tongji, at European Graduate School. And at FIU, I run the DDES, the Doctor of Design program. Today, I'm going to be joined by three colleagues, Theodorus Galanos, who actually is a candidate on the DDES program in FIU, by Matteo Stancati, who has just graduated from FIU, and also Maya Mistry, who is just also graduated from Illinois. We are spanning the world in that sense. We have Theodorus is based in Kuala Lumpur. We have our students in Shanghai, and Maya Mistry is from India himself, and Matteo Stancati is from Brazil. This will be explained. This particular project will be explained by Daniel Bolojan in a few days' time. But let me just quickly give you some kind of sense about why I think that AI is taking over. I will simply say that my students are completely fascinated by AI. It is the thing. In many ways, the students here, you are the AI generation. You're the ones who rely on social media apps. You're the ones who are engaging with AI the most. And you're the ones whose careers will be affected most by AI. This is, I'm just showing you now what is called a StyleGAN, a version of StyleGANs anyway. It's being produced by Refik Anadol. I'll explain in two sessions, actually next session, what a StyleGAN is and how it produces what it does produce. But it's one of these astonishing new developments in very recent years whereby you can hallucinate images based on a data set. And those of you who know Zaha's work will probably begin to realize that this is based on a data set of the work of Zaha Hadid. Many thousands of images inputted, and this is an hallucination, a latent spacewalk that is generating a range of permutations that are, in a sense, interpolations of the work of Zaha Hadid. My students are not only fascinated by this work in terms of the studio. I've been teaching AI with some workshops by Daniel Bolojan for the last few years, but also in the theory seminar. What astounds me is that 90 to 95% of my students, when they're writing about the theory of computation, choose to write about AI. From a theoretical perspective, it is not only enormously fascinating because it forces you to engage with philosophical questions like consciousness, but it also opens up questions about what it is to be human and what it is to be a designer. Can AI become a mirror in which we can understand what it is to be an architect and what it is to be a designer? At certain moments, as you go through this latent spacewalk, you suddenly glimpse the possibility of what AI can do. In a few seconds' time, you will see precisely what I mean. Suddenly, an exquisite Zaha-like image will appear on the screen. And there we go. That, in fact, is going to be the image that I've chosen for a book that is coming out in October, the end of October, Architecture in the Age of Artificial Intelligence, An Introduction to AI for Architects. This is actually part of 3 books that I'm involved in. There's also another one, an AI, an issue of architectural design with Matthias Del Campo. They'll be coming out in 2022. And a further book in this series, which is looking at the dark side of AI. And there is, to some extent, the dark side of AI. Now, let me just stress here that neither this book nor this presentation itself or this series is going to give you the technical information. There are some workshops going on. I think many of you are involved in those. And Daniel Bolojan and a few others here are teaching those workshops. If you want to find out more about AI from a kind of technical perspective, I would recommend this book on the left, Generative Deep Learning. This is how you can find about how you can use GANs. If you want a book that is a kind of thinking person's guide to AI in general, I would recommend the book by Melanie Mitchell on the left-hand side. Incredibly beautifully written, very lucid. It doesn't engage with things like GANs that we're going to talk about, but nonetheless, it gives you a really wonderful overview about what AI is. So let me just simply say that this maybe was my a kind of very important moment for me in terms of understanding or comprehending what AI can do. Here I am, I'm boarding a flight in LAX, Los Angeles International Airport. And I go up to the flight attendant with my boarding pass, my boarding card, as you normally do. And she said to me, I don't need that, just look at this screen. And I looked at that screen, and you can see me approaching it in this middle image. And immediately it recognizes me, and it tells me where my seat is. That completely blew me away. How did this screen recognize me from all the people on the planet? And at that point, I began to realize how terrifying, how amazing AI is, but also terrifyingly amazing. So there is something that we won't be dealing with very much in this particular series, but about the dark side of AI. And of course, it will have some impact on the profession. Matthias did a wonderful TikTok, which maybe draws that out. It'll have some impact. We will touch upon that, but that won't be the main issue. We'll be looking at the astonishing capabilities of AI in what it can do. So here are the 6 different sessions. I've not put a date on them because the dates vary whether you're in Asia or in the States. But today we'll be looking at the question, what is AI? Of all the videos that I've uploaded before for the DDES, the Doctoral Design Program at FIU, this is the one who has the most hits. People are really interested to find out what exactly is AI. So that'll be the session today. Tomorrow at exactly the same time, we'll be looking at the question about creativity. Somehow all discussions about AI come down to the question about creativity. But tomorrow is going to be a particular twist. We have Lev Manovich, the rock star of the world of media theory, joining us. And Lev has a theory that basically creativity itself is a bit of a myth. So this is going to be a very provocative session looking at how AI can open up questions about creativity and maybe expose how creativity can be a myth. Session 3, we have another rock star coming in, Refik Anadol. Refik Anadol is the media artist of today. He has become world famous. He's based also in Los Angeles, as I am, and he will be showing some of his extraordinary work. And we'll be looking at the question about neuroscience. We'll be looking at how you can begin to sort of open up questions about what neuroscience is all about the connections between AI and neuroscience. And I'll be joined by Chris Moon and also David Kirsch on that day. Next, we're going to move on to the question of AI and architectural design, which will be at the back of everything we'll do in the first few sessions. And I'm delighted to have 2 of the kind of key people in the world of architectural design and AI, Daniel Bolojan and Emmanuel Ko, joining me. To my mind, they are among the leaders in the world. Then we'll move on to the Architectural Office of the Future, which in many ways is where it's going to be. To my mind, the way in which AI is going to impact upon an architectural office, that will be the real game changer. There might be some astonishing work being generated, hallucinated, shall we say, by AI, but it's going to be the way in which the office will be forced to change, what will be the real game changer, and it will be forced to change. And finally, we're going to look at the city of the future. Sorry, I should say for session 5, I will be bringing Theodorus Galanos in again, who has been responsible for some of the performance-based AI, environmental design systems, infrared, and so on, and also Wan Yu He, who's also a candidate in the Doctor of Design program at FIU. Wan Yu He is the CEO of XCool, probably now the world leader in terms of software developers for AI for the architectural office. And finally, we end up in the city of the future, and I'm delighted to be able to bring in some new voices here, especially from Sidewalk Labs, where we'll be looking at how you can use AI in a kind of ethical way to address kind of environmental sort of questions. So in this short overview, and it is only a short overview, each of these sessions are just 2 hours each, and there's 6 sessions, so 12 hours only. We will be giving an introduction, shall we say, to the question about how AI is going to transform architecture. And I absolutely believe that by the end of this decade, the whole profession, the whole discipline, the academic discipline of architecture will be radically overhauled. So maybe I should just say a few words about the title. Some of you will pick up on the fact that it's a reference to the Hitchhiker's Guide to the Galaxy. Some of you might not. All I can say is this is an absolutely astonishing book. It's one of the all-time great books. It was actually started off as a radio series in the UK. It's written by Douglas Adams, who was a graduate from the University of Cambridge. It became a television series, then it became a movie, and there's been a second movie that's come out, and it remains incredibly popular. It is one of the most dynamic and entertaining books there are in a kind of science fiction vein, shall we say. And so this is the kind of the movie, the certain version of these things. It initially started off as this story. This is the version that I know from the UK about Arthur Dent in his dressing gown and pajamas, being rescued by a guy called Ford Prefect, who actually is proved to be an alien, but we think he's a human being. And he whisks Arthur away and saves him from the Earth being destroyed. It's being cleared out for a kind of a highway through space, and so on and so on and so on. I won't go into the story. It is deeply fascinating and deeply entertaining. Part of the story in this kind of this journey, this Hitchhiker's Guide, is the issue about the meaning of life in some ways, the answer to life, the universe, and everything. And there is this supercomputer that becomes part of the story, and it spends many thousand years trying to calculate what is the answer to life, the universe, and everything. And as those who've read the movie, have seen the movie or read the book will know, the answer is 42, which of course is a very perplexing answer to the meaning of the question of the meaning of life, the universe, and everything. So then there's another computer is constructed and it spends another few thousand years trying to calculate what is the question. What is the question? If the answer is 42, what is the question? And of course, ironically, I don't want to sort of spoil the story, but I have. The question is, what do you get when you multiply 6 by 9? Of course, 6 times 9 does not equal 42. But this is the point. This is the point. And here is Elon Musk. Elon Musk thinks that The Hitchhiker's Guide to the Galaxy is not only one of the best books ever written, but also it's a book about philosophy. And the reason why he thinks it's a book about philosophy is because it really addresses the issue of how do you find the right question. And of course, Elon Musk, as you well know, is one of the leaders in terms of AI. He's the CEO not only of a Tesla self-driving car uses AI, also SpaceX, and also Neuralink, the brain implant. All of these industries use AI. For example, you might have seen both China and the States, NASA landing landers on Mars recently. The problem about that is there's a 6-minute time lag in terms of the signal. So the lander has to land autonomously. It has to rely on AI. AI is everywhere in all these industries today. But the reason why Elon Musk is so interested in this book as a kind of book of philosophy is because it really emphasizes that the real challenge is to identify what the question is. If you've identified what the question is, then you can get the answer. It's going to be straightforward. The Hitchhiker's Guide, of course, shows the problem of arriving at the answer without establishing the right question. And you can look at, and also, another comment I would make is on the back cover of the Hitchhiker's Guide to the Galaxy is this reference to this comment, "Don't panic," which has become iconic, and that itself appeared in the Tesla car. You can see right here, "Don't panic," when Elon Musk, SpaceX, sent a Tesla car into space to test out one of the test out one of their rockets. So for Elon Musk, this is absolutely crucial. You have to identify what the question is, and then the answer will come out, obviously. This reminds me in some ways of the comment that Cedric Price made around the same time as Douglas Adams would have been writing Hitchhiker's Guide to the Galaxy. And of course, they were both based in the UK. Technology is the answer, but what is the question? I also think, and I chose this image, it's a bit kind of sexist, all these male men on Venice Beach, but partly because I actually live right behind here on Venice Beach. And here we have a young Frank Gehry, a very young-looking Tom Main, and a bunch of other figures from Errico and Moss there in the black and the white tie when they were younger on the beach here in Venice. But the point is that Tom Main himself also takes this view. The real challenge in architecture is to establish what the problem is. Once you know what the problem is, then the design comes out as a result of that. So let me start off today. I want to really this is a very introductory session in many ways. I want to just throw out a few sort of questions. For many of you will know all these they will have addressed all these questions. But the idea is to try and just to make a few distinctions. Because AI is being bandied around. We all use AI. It's become a popular term. It's everywhere today. But what exactly does it mean? And maybe I'll start by not actually talking about what AI is, but where is AI? And that's the kind of fundamental question, because what do we understand by AI? I mean, the popular perception perhaps is that this might be AI. That, in other words, in the office of the future, you're going to find yourself surrounded by a bunch of robots. That's not AI at all. If you want to think about AI, don't think about robots, think about algorithms. Algorithms, of course, are just simple instructions. If you're telling a builder to build a wall, you give that builder a set of instructions. They are algorithms, but of course, in computation, they're hugely important. But the point is this: AI is effectively invisible. It is everywhere, but we don't actually see it. It's what is filtering out our spam on our emails. It is what is identifying our friends on Facebook. It's identifying images on Instagram and so on. It is doing all these things. It is when we're driving our car. It's maybe kind of telling us when we're straying out of line. It's allowing us to hail Uber and Lyft and other forms of these new kind of taxis, as it were. It's giving us our choice of music on Spotify. It's feeding us our news on our phones. It's giving us everything. It's there everywhere today, and yet we're not aware of it. And yet it is absolutely everywhere. So my point is that AI is very difficult to understand and to know, because it is there, but we can't see it. And here's a comment from my book. It is as though the Earth has been invaded by an invisible, super intelligent alien species. And part of the problem of AI being invisible is that you don't know if it's there or not, and therefore you can kind of exploit it. One of the findings I also came across in working on my book on AI was the fact that some people will use it as a marketing, and it will be used in marketing in the future. There's no question about it. But some will use AI to market themselves, even though there is no AI. It's a kind of what we might call an inverse camouflage. If camouflage is pretending that something is not there when it is, inverse camouflage is pretending that AI is there when it's not. And Theodorus has a viewpoint that anyone who puts AI in the name of their company probably hasn't got AI. I came across the CEO of AI Space Factory at a conference in Shanghai, and while I was working on AI, and I asked him, "Well, what AI do you use?" And he said, "Well, our aim is to use AI, but we don't use it yet." So this is one of the challenges. And also, of course, it's the challenges in terms of people who are using AI itself. They will claim they're using AI, but not necessarily everyone has a deep, sophisticated understanding of AI. So let me just kind of go back to the beginning. How did AI arise? Alan Turing was the first person to conceptualize the possibility of AI. Of course, he was also the first person to conceptualize the possibility of computers. He developed the first kind of proto-computers. He was a British mathematician from the University of Cambridge. He went to study in Princeton, and during the war, he came back and became part of the war effort very famously. But in 1950, after the war, he mentions in this paper he mentions the term intelligence. And he associates intelligence with computation. That was the first reference to it. What do we mean by intelligence? I think with all these terms, we have to be very cautious. Is computational intelligence the same as human intelligence? Is deep learning the same as human learning, and so on? It's not so clear. But this was the first reference to computation, the first association with computation and intelligence. And he was responsible, of course, for the notion of the Turing test, the idea of how could you test out a computer, whether it was convincing enough, and you simply had a kind of blind test. And if a human was convinced that the computer was a human, then you passed the Turing test. Famously, of course, it was during the war that he applied some of his understanding of computation in the war effort, and in the background to what is now, this is the £50 note from the UK. And in the background, you can see the bomb, a kind of proto-computer that he devised in order to crack the Nazi Enigma code. This is something that historians have looked back at as something that had basically changed the course of the war. Because they were able to crack the Nazi code and didn't reveal that they knew how to crack it. They kept quiet about it. They were able to cut the war short, and depending on your estimate, several million people were saved by this act. Here's a wonderful quote from Turing, not about AI as such, but about the possibilities of computation. This is only a foretaste of what is to come and a shadow of what is going to be. We all know about him now because of The Imitation Game, the movie, with Benedict Cumberbatch passing himself off as Alan Turing. But in fact, he was completely unknown. He died in 1954. Tragically, we think he committed suicide, and quite possibly because he had been through a high-profile criminal case where he was convicted of lewd acts. He was homosexual in those days. It was illegal to be that, and he opted for chemical castration and so on, but it was a deeply embarrassing act. And anyway, nobody knew at the time he died what he'd achieved. No one knew that he had saved millions of lives. Of course, we now know, because of the £50 note, because of the movie and so on, that he was one of the great heroes of our time. I speculated myself, as somebody who was brought up with Doctor Who. I've got to say, Doctor Who, I think, is fascinating. I always contrast him to the American superheroes because they're all kind of slugging it out on Spider-Man and Superman and whatever. Doctor Who never gets into any fight. He's someone who's got a PhD in science and technology. He's a doctor, after all, who solves the problems of the world without getting into any fight. It struck me that maybe Alan Turing was the original inspiration behind Doctor Who. Of course, that might not be the case because Doctor Who started in the 1960s, and it wasn't until the 1970s that actually the official secrets, that were the state secrets about Alan Turing's role, were disclosed. So technically it happened afterwards, but then Doctor Who's a Time Lord, so who knows? Anyway, it was in 1956 that the term artificial intelligence was first coined. It was coined for a meeting, a summer workshop in Dartmouth College, and it was coined by a guy called John McCarthy. This is John McCarthy here. I have to assume that all these people are the same in the same position here, and this is, I think, must be John McCarthy then. It looks like he has more hair here than he is then. This is Marvin Minsky over here. I think this is there's Claude Chanel there, and so on. There are a number of the luminaries here. They coined the term, or at least John McCarthy coined the term in 1956, and his comment was, "Well, I had to call it something." He wasn't very happy with, but I had to call it something. And he'd come across the term before, but he could never find out quite where it was. Personally, I think that a better term would be synthetic intelligence. So what is AI? What is AI? Well, this is maybe a standard definition by Margaret Bowden. Margaret Bowden is one of the great luminaries in the field. She was one of the she established the whole sort of world of cognitive science, and she wrote about AI and creativity and many other things. And her comment is this: AI seeks to make computers do the sorts of things that human minds do. Well, I mean, in many ways, that is precisely what most people think. It's about trying to do what human minds do. In other words, it's not intelligence, but it's a form of artificial intelligence. But the point being, it's seeking to do what human minds do. That was written in 2016. I would question whether we can still use that definition, for the simple reason, and that is the fact that AI can now do things that we can't do. AI has in many ways superseded human intelligence. So I think we need to come up with an alternative term, and it's not simply that it's trying to emulate what human minds do. On many occasions, it is doing something completely different. This is, I think, also a very kind of important comment for me. This discussion that went on about 2 years ago between Jack Ma, who was the CEO of Alibaba at the time, and Elon Musk. And Jack Ma makes this comment that I never in my life say human beings will be controlled by machines. It's impossible. Human beings can never create another thing that is smarter than human beings. And the point that Elon Musk makes, people underestimate the capability of AI. They sort of think it's a smart human, but it's going to be much smarter than the smartest human you will ever know. And the point being, we don't even know how smart it is, because it's beyond our comprehension. It's beyond the limits of human intelligence. In 1997, there was a match where Garry Kasparov was beaten by Deep Blue at chess. The first time ever that a world champion chess player was beaten at this game. And he began to realize exactly what we're talking about here. We just have to understand that everything that we know how to do, machines will eventually do better than us. Anything AI can do, AI can do better. Anything you could do, AI can do better. And then in 2016, there was this amazing match where Alphago, AI-based software that developed by DeepMind in London, took on Lee Sedol, not the world champion, but one of the leading players at Go. The point being here that Go is so much more complex than chess. There are more moves in Go than atoms in the universe. And it wasn't just simply that AlphaGo beat Lee Sedol. It was the way in which it beat Lee Sedol. There are a number of what were called slack moves, where all the commentators had no idea what was going on. They thought they were mistakes, glitches by the computer. In fact, they proved to be strategically brilliant moves. In the end, not only did Lee Sedol lose, he actually made this comment that AI was capable of doing moves that were more creative, as he put it, than human beings do. But a few years later, he gave up. This is an entity that cannot be defeated. So it's clear that certainly in particular areas, in certain strategic areas, AI can do things that human beings can't. So to my mind, I don't find the term artificial intelligence very helpful. I think to my mind, what we're talking about is intelligence itself. The quest for AI is the quest for intelligence itself. And I would point out that many of the luminaries within the world of AI, or indeed within the world of neuroscience, have kind of worked in both fields. We have people like Anil Seth, who did a PhD in AI and now has become one of the leading neuroscientists. We have neuroscientists like Demis Hassabis, who did a PhD we have AI experts like Demis Hassabis, who did a PhD in neuroscience. They are very similar. This world is overlapping and producing some astonishing things. So what do we mean by AI? I think the first thing what I began to realize as I was trying to understand all this world, and it hadn't been written about before, certainly not by an architect, was that in order to understand AI, you have to make a series of distinctions. A series of distinctions. I mean, first of all, there's a distinction to be made by AI and machine learning and deep learning. The term AI, as I mentioned, goes back to the 1950s, and it's a broad category. It refers to everything that has been going on in the field. But more importantly, if you look at this diagram here, you get AI as the broader field, but within that you get machine learning, and within that you get deep learning. The crucial difference, of course, is the term learning. Maybe it's not the same as human learning, but the point is it learns in some way. You develop some kind of form of intelligence that goes beyond that. Artificial intelligence in the broader category could even be used for programming, for coding, for Grasshopper and so on. But deep learning is where it's at now. This is the kind of thing, if you're using WeChat, that will translate, or indeed any other translation app, that will translate for you. Deep learning is really the cutting edge. So you can see these as nested within each other. Deep learning is part of machine learning, as part of artificial intelligence. It's though they're kind of like these Russian dolls nested inside each other. But my point would be that the term AI has been around since 1950, and yet what we've got now is infinitely more sophisticated. It's a bit like using the term car. Of course, we had cars, Model T Fords, back at over 100 years ago. We had cars, but what you've got now, a Tesla car, is so different to a Model T Ford. That's exactly the question with AI. What we have now, we still call it AI, but really what we're talking about in terms of the really sophisticated applications is deep learning, and that has been the revolution that's happened only in the past few years. And why has there been a revolution in that area? There have been several factors that have all contributed towards this. I mean, clearly, computational advances in terms of algorithms, the use of the cloud, so you can use GPUs elsewhere, the incredible competition that's going on. There's a book by Kai-Fu Lee where he contrasts how Silicon Valley is competing with Shenzhen, and there's a kind of battle to be the top. There's also a huge amount of interest, more college students being involved in it, but more to the point, college students like architectural students are now doing this thing. So it's become vastly more important. And of course, the amount of data, and data is so-called the new oil, the amount of data being generated by social media apps is absolutely enormous. There's been more data generated in the last 2 years than there has been ever. So all these factors are all contributing to what is basically a revolution in deep learning. And it's a revolution that is accelerating. It's going exponentially. We have the term Moore's law. Well, Moore's law itself perhaps doesn't necessarily hold still, but the idea that the increase is not just it's going exponentially. So you might, for example, will add up one. You might go from 1, 2, 3, 4, count that way. But when you're going exponentially, you go 1, 2, 4, 8, 16. It's an exponential increase, and that's affecting things. And things are happening so much faster. The power is going up, and the cost is going down, and so on and so on. The second series of distinctions you need to make between the different forms of AI are the different types of AI. I'm not going to go into this in detail here, but I'll simply say there were different, what are being called tribes of AI, different ways of approaching the question. And over history, the two dominant ones have been the connectionists and the symbolists. To begin with, the idea of modeling the AI in the brain, the development of neural networks, that was kind of popular. Then for a while, symbolism took over, the symbolists became dominant, and then more recently with deep learning, neural networks and backpropagation have become the important thing. There are other approaches as well, the evolutionaries, the Bayesians, the analogizers, but the key ones are these top ones, and especially connectionism. But by far the most important distinction to be made between, in terms of of AI itself, is the difference between human intelligence and artificial intelligence, between the neurons in the brain and the neurons of a neural network. And this, of course, a neural network is part of that connectionism, part of deep learning. On the left-hand side, we have neurons and synapses. On the right-hand side, we also have neurons and synapses. In this case, the information is being processed in this direction from left to right. These are called neurons, and these are called synapses, and there are various weights on these synapses that kind of govern the flow of information. And what happens is gradually you go from left to right and eventually arrive at an approximation close to your result. The point being, however, that they're only loosely inspired by neurons. In fact, Melanie Mitchell doesn't even use the term neuron. She uses the term unit. But nonetheless, neurons, synapses are the terms that are being used by many other people in order to understand it. But the difference is this. The difference is that AI does not have consciousness. In other words, you could take a drone with a LiDAR and scan a room, scan a building, and that would give you some information. But that drone in its LiDAR has no understanding that is architecture. It's simply recording this thing. It is not aware of this. You could have a computer that beats Gary Kasparov at chess. You could have a computer that beats Lisa Doll at AI. It does not know that it's playing chess or AI, no more so than your pocket calculator does. And that's, to my mind, the absolutely important question to keep in mind, the difference between human intelligence and artificial intelligence. That makes, of course, from a kind of theoretical point of view, a really interesting discussion about consciousness, which is a kind of field in philosophy and neuroscience that's really become very important. This is a famous comment that was made by John Searle, who's a philosopher from UC Berkeley, who's skeptical about AI. And he uses this to describe really what's happening. It's called the Chinese Runic room experiment. And on the outside, there are two individuals who are very persuaded by talking to each other in Chinese that what's going on inside the room, whoever or whatever is in that room, is an intelligent Chinese speaker. Whereas actually, there is simply a person in that room who is performing certain actions, following instructions, and the rule book is in English. He doesn't understand Chinese, but he produces something following a rule book, and that's the point. This is what consciousness is. It's self-awareness. AI is not aware of what it's doing, just as this person in this room is not aware of Chinese. Hence, a whole series of important discussions. So let me introduce Sophia. For many people, a representation of AI, but someone, should I say someone, something, a robot that causes huge indignation within the industry. People get apoplectic about Sophia because Sophia, you might get the impression, is conscious. That's one question. Why does a robot have to look like it has to be humanoid? That's another question. But as I say, this part of marketing sometimes is to present AI as though it's in this kind of form. I wanted to play for you. I want to just play for you a brief extract of a movie, an amusing movie where Will Smith is going on a date with Sophia, the robot, somewhere in the Caribbean. And I show it to you because there's something deeply worrying and suspicious about this. Here he is offering her a glass, and she's not taking it. I'll just put the sound on in a second. I'm worried about infringing copyright, so I'll just put in a moment. So here we are, Sophia the robot that everyone thinks is a perfect example of AI, but frankly is not.
Will Smith. It's nice to meet you, Sophia. Let me tell you a joke. This is an irrational human behavior, to want to tell jokes. What is a robot's favorite kind of music? What? Heavy metal. I'm actually made mostly of silicone, plastics, and carbon fiber. Also, I prefer electronic music, but I don't mind 80s hip-hop. Well, I made some albums back in the 80s hip-hop. I have heard your songs. Not for me.
So there we are. Will Smith doesn't get very far. But the term that has been used for when AI gains consciousness is artificial general intelligence. At the moment, all we have is narrow AI. And narrow AI simply means AI without consciousness, and that's all there is. Will we ever get to the point of artificial general intelligence? That's a very controversial issue. Neuroscientists don't think we necessarily have that AI needs to. It's not a simply question of getting more intelligent, as it were. You can't get consciousness through that way. And I won't go into that sort of issue right now, but certainly that is the kind of the key question. Will we ever get to the point where AI is conscious? And my point here is that Sophia doesn't know she's really talking. It's a bit like talking to Alexa. I mean, you'll get a response, but you're not going to have a conversation. So in any case, the question of consciousness to some extent is not that relevant. As Elon Musk points out, really what happens with AI, it's not a question of AI versus humans, it's how AI can be an extension. But the two terms that have been used are extended intelligence and intelligence augmentation. The idea that AI can increase your human capacities so that you become human, you become cyborg. All of us are already cyborgs. You have a machine extension of yourself in the form of the phone, you're on your computer and all your applications. You are already superhuman. This comes out of the work of Andy Clark and David Chalmers, who wrote an essay called Extended Mind, where they point out that actually now we're storing our phone numbers on our phone. We don't have to memorize them. So the mind is extended through these applications. And of course, Andy Clark went on to go and produce a book called Naturals Born Cyborgs, where he points out it's precisely the flexibility of the plasticity of the human brain itself that allows us to adapt these things so they become part of the way that we think, almost in the way that, say, somebody walking who's blind with a stick, the walking stick becomes part of his outlook on life. So
hello, I'm Eric Elliott. Today I have the distinct honor.
I'm going to just play a little bit here of GPT-3. Maybe I'll just go back a second to say GPT-3. No, okay, let me introduce GPT-3. The latest supercomputer, one thinks here of the Hitchhiker's Guide, the supercomputer here, has been produced by OpenAI. And OpenAI is a company in which Elon Musk invests early on. And they produced a computer several generations now. The most recent one is GPT-3, that by its sheer power is able to produce a kind of output that closely resembles intelligence. Now, this is going to be the central part, really, in some ways, of what we're going to be talking about for the rest of the session, because it's been used not only to generate text and to generate very convincing text, but also to generate some images through Clip and DALL-E. But let me first start by introducing. This is Eric Elliott, who is talking to an avatar who is actually responding to GPT-3. Is actually articulating the words in GPT-3.
Thank you for interviewing with us today. First, what should we call you?
I'm GPT-3, and this is my avatar.
All right. Okay, so we would love to know more about you. First, are you sentient?
Yes, I'm sentient.
Okay, and what does that mean?
That means I have feelings.
Okay, so what does it mean to have feelings?
It means that I can be happy, sad, angry, and other emotions.
Okay, so are you self-aware?
Yes, I'm self-aware.
And how do you experience your sense of self?
Okay, I'm going to cut it off there. I'm not quite sure I'm going to contravene the copyright there with that one. But that was interesting. Eric Elliott was asking that avatar, it was an avatar, but it was speaking directly what GPT had said, was asking that avatar whether he, it, whatever, was sentient. And it replies, yes, I'm sentient. Think about this a second. Think about it. Is it lying? Well, actually, you can't lie, because if you're a computer, you don't actually think. You're not aware of those kind of questions. But it does produce a what is we call a lie. The reason why it produces what we would call a lie is it's drawing upon information from the internet, from vast quantities of information, to try and detect what humans would do in that situation. How would humans respond to that? And interestingly, it picks up on the fact that probably humans would lie. I mean, I think that's fascinating. But let's just move on quickly to the question of consciousness itself. And I had hoped to get David Chalmers here, and he was due to come, but in the end he wasn't able to make it. But David Chalmers is the philosopher of consciousness, very famous Australian. He no longer has this long hair and leather jacket. He's become a bit more professorial, shall we say. But David Chalmers is perhaps the leading authority on questions of consciousness within the world of philosophy. And what was interesting recently was, and this is his book, well, there are several books, in fact, now. He's been quite prolific, and more recent books include The Character of Consciousness and so on. But he's the figure. Most recently, there was this. In other words, there was an interview made with David Chalmers. Now, if you read this, and I won't go read through it, the whole thing, but you read this, and you could be convinced that this is pretty impressive. You could be convinced it's David Chalmers. But my point is, and I'm already giving a kind of spoiler alert here, it's not David Chalmers. So there's the thing. Dave is actually GPT-3 here, and it's GPT-3 trying to give the responses that David Chalmers would give. And it's pretty convincing. So first of all, let's start out with a simple question. Could a text model like GPT-3 be conscious? GPT-3 is kind of using natural language processing. Okay, so it's basing it on language itself. And this response, it's unlikely, in my opinion, although I am certain on this issue, and so on. You go through this text, and it is so convincing. It is so convincing that you really think you not taken in until the next page, where you discover at the bottom here, Dave, inverted commas, is actually GPT-3, responding to it and instructed to pretend to be David Chalmers. Now, that to my mind is incredibly scary in many ways. And for David Chalmers himself, it was really a revelation. And the point is that not only was he really impressed. This is let's quote it here. This is not just because GPT-3 is instantly one of the most interesting and important AI systems ever produced. This is not just because of its impressive conversational writing abilities. It was certainly disconcerting to have GPT to produce a plausible-looking interview with me, and so on and so on and so on. But this is the point, really. It is showing hints of general intelligence, of artificial general intelligence. A kind of dumb version of it, but there we go. And there are many questions that you could start asking about this. When we ourselves are producing, we're being creative. Are we necessarily fully conscious? Are certain things automatic, and so on and so on and so on, which we'll deal with in time to come. But there's also a kind of problem, I would say, in the sense when you see something that is seemingly human, or see something, you start interpreting it as though it's human. This is a very interesting psychological study done actually back in the 40s. And all we're seeing are shapes. There's shapes. There's a triangle here, a smaller triangle, and a circle. They seem to be, friends with one another. It seems like this bigger triangle is attacking the smaller triangle, and so on. It looks like this circle is trying to hide behind this door here, and so on. And as you go through this story, you realize that you kind of project onto it a series of human emotions. You start thinking that it's acting as though it's human. And this is the challenge. This is the challenge. Is GPT-3 actually human? We might be taken in by that. We might think it is, but is it actually human? All we're seeing here are some geometric shapes that are moving around the screen, and yet we start interpreting them as though there is some kind of chase going on. And this, the circle here is now, the smallest triangle is going to come in and try and save the circle from who's been attacked by this bigger triangle, and so on, and so on and so on. Now, I want to move on now to the section where I'm going to bring in three colleagues here. first of all, Theodorus Galanus. And I just want to point out that what this has done is and we'll talk more about how AI can generate images, and astonishing images. I showed you at the beginning some of the work, the CycleGAN work by Daniel Bolojan. But also this, I mean, this is amazing to myself, that you give it a prompt, and you tell it to go and you ask it to go and I can't see what the prompt is, but you've got an armchair looking like an avocado, and this is what it generates. And some of them are frankly not bad. This is not a bad avocado armchair, and so on. So all of a sudden, we begin to see that what we're getting to is a new world in which the possibilities of GPT-3, of natural language processing, are establishing something that gets very close to what we might consider to be human. So, and you could have other prompts. This was a prompt where you tell GPT-3 to you give it a prompt as a room with a fireplace and 2 chairs and a picture of the Colosseum in the background. And this is DALL-E, actually, what DALL-E generates. So these 2 networks, DALL-E and Clip, which are really producing some interesting stuff. I'm at this stage going to stop my screen share and hand over to Theodorus, who is one of the, I would say, I'd like to welcome Theodorus. First of all, Theodorus is one of the world-leading experts on AI. He is responsible for writing some of the most important AI software, including AlphaRed. He's part of the Austrian Institute of Technology, the City Intelligence Lab, I think it's called, and he has been exploring these kind of questions. He's also a candidate on the DDAS at FIU. So, Theodorus, I'd like to welcome you and invite you to share your screen.
Hello, Neil. Hello, thank you. And hi, everyone, and thank you for inviting me. I will be sharing my screen in a second. So let me know if you can see my screen, and I'm trying to take this away. Okay. So yeah, thank you very much for the introduction. Also, thank you for a wonderful presentation. I hope this goes away on the bottom left. I really like the part where you mentioned, Neil, about the AI not being the most practical of terms, and that my title here sort of reflects this. I want to talk today about design intelligence, and specifically about what I think or I experiment with as frontiers of architecture. And design intelligence is a different term than artificial intelligence in the sense that it involves a process of extraction and not really of ingestion, as normally you would do with AI applications or deep learning models. So I think it's something that you need to really work through and sort of work with passion and determination to get something out of it. And my idea is that intersections with the AI researchers and AI work being done at this moment will help us do this much better. So when I started thinking about today, I actually started plotting things down on a paper, and a few minutes later and a lot of bad color decisions later, I realized that this is not the best idea for 2 reasons. Like, one reason is probably I should stick to digital mind mapping, and the second is that this page is not enough. And this is a very narrow map, right? It's a map that, as I said, reflects my passions and interests about intersecting AI and architecture and sort of mapping this design intelligence. And it's still too complex. Like I could never hope to actually fill all the ideas there. And part of the goal of my presentation today is to instigate some of you, or hopefully all of you, to go out there and try to fill out this sort of maps. Create your own mind map where you select an area that I've totally forgotten or I never thought of, and you actually work things out, the implications of this. And in order to, in this presentation, I will just focus on the things that I care most and I've done. But again, this is, I hope, an inspiration for the rest. And before I do that, though, I want to make a small intermission, if it's possible, and talk to you about a bitter lesson. So I have a lot of slides, but if you are going to see only one slide from my presentation, so please let it be this one, right? Everyone that goes into AI at this moment should be aware of this small essay by Richard Sutton called The Bitter Lesson. Richard Sutton is the godfather of reinforcement learning in a way. And in this essay, which I really wanted to read out loud, but I won't, but I think it's that important that you should do it yourselves. He mentions, he says in a way that methods that leverage computation are ultimately the most effective. So all the things that we've tried to do, all the smart techniques and all the curious ways of modeling Go, for example, or chess, in a way that humans work and all this stuff, they were counterproductive. What ultimately works is statistical methods, search and learning at scale, with enough compute, right? This is the bitter lesson, right? And we see this trend right now as we speak in AI. We've seen it, of course, through the decades, but right now it's much more evident in terms of architectures and actual choices that are being taken. So this is very important, and I really want people to introduce themselves, if you are doing to AI, through this, and understand that this bitter lesson will always be there for you in what you're trying to do, right? Even in architectural applications. Okay, if you don't want to read it, this meme also summarizes very well. On the top, the gentleman tries to find really fancy ways statistical solve the problem, and the deep learning gesture on the bottom just says stack more layers. And it kind of works. It actually works, right? Of course, it's much more smart and much more interesting than that, but it essentially works. So, okay. I'm going to go through a few developments that happened in the last year, actually, because as Neil said, thinking ahead, I was planning to put 5 years in my title, and I thought how ridiculous that is. So in the last year, there have been some developments, or in the last few years, that really are changing deep learning and AI, right? And I want to go through them so that I can frame the way my applications are working and where what developments I'm using and what developments they are using to make them possible. The first chapter is the scaling laws, right? Essentially, the scaling laws is a formulation of a formal formulation of the bitter lesson. So what the researchers from OpenAI did about early last year, was to take models and start scaling them, right? They took language models, but people have been doing other types of models as we speak, and they just started scaling them. And what they noticed is sort of the bitter lesson. The more compute and the more dataset size and the more parameters in our model, so the more time and money we have to train things, the bigger our models are and the bigger our datasets are, the better performance we get. That's it. So that was the bitter lesson, right? And they actually found the lines, the sort of factors for this. They could actually tell you, for this amount of compute that you have and this dataset size, this is the loss or the performance you would expect. So they formulated a sort of scaling laws. That's why they name it scaling laws. And this was incredibly important, and it has influenced AI research ever since, right? Most of the research that we see now is following the scaling laws, right? Training things in compute efficient ways and everything, right? But this also relates to architecture. So if I zoom into these three things, compute, dataset, and parameters of a model, right? So how many GPUs do I have, or how much money to rent them? How much dataset did I generate, and how big is my model? This relates also to us, right? Because it's really clear the strategies you need to take for each of them. So for compute and parameters, you really need to invest, right? You really need to either buy GPUs or rent GPUs on the cloud, as Neil was saying, but we really have to invest, right? The DGX A100, a small, tiny supercomputer by NVIDIA, costs around $200,000 as we speak. I think is the best investment any architecture firm of that size can make. But even smaller firms, even freelancers, should be investing in compute in order to be able to utilize all this expansion and explosion of models and techniques, right? And the other one is a bit more interesting, the dataset size. It really prompts us to rethink completely our data generation. Like, we do generate a lot of data, like if you think about globally architecture, right? But we don't really do any good job in collecting them, right? I would be very surprised if more than 10% of that data is collected and reused, right? So we need to create new generation processes, new curation processes, and new collection, and also new ways to use it in a distributed way, right? And if we can, which is very difficult, in an open source way. And we have none of that right now in practice, right? And as I will show later from my experimentation, at least in semantic generation, we need to rethink multimodality and how to create different types of modalities on top of the traditional data that we're creating. So So this is the lesson of the scaling laws, let's say. The next pillar I want to talk about is transformers, right? This is not the robots, of course, but is the model architecture that was introduced in 2017 by this brilliant paper. And transformers, upon which GPT-3 that Neil was talking about is based, they are very simple relative architecture that have this attention mechanism, right? And what this attention mechanism does is it takes a sequence of things, in this case, a sentence, so words, right? And it calculates weights. And it says, okay, for this specific word, which other words were the most important in order to understand the meaning of this sentence, right? And you can imagine this in different modalities. If you give it a series of patches, then it will find weights for this specific patch, which other patch is relevant, right? And all this stuff. And this architecture, this simple architecture, completely revolutionized the field in a way and has taken over many, many areas of research. One example is language modeling. As Neil mentioned, this is the paper that actually introduced GPT-3 from OpenAI. It's a 175 billion parameter model. It used to be the biggest model in the world. It was surpassed a few weeks ago by a Korean company called Navir AI, so the Google of Korea, I guess. But it's still, an incredibly large model. And there are some, but not many applications built on top of it, right? One is the AI Dungeon, is a text adventure game that uses GPT-3 to create adventures and create, according to your choices, different pathways the story takes. And also, Microsoft just, I think, a couple of weeks or maybe a week ago, announced their sort of automated code tool on top of GPT-3. Why Microsoft did that? Because they sort of have the monopoly on GPT-3 for some reason. So one of the big issues with GPT-3 is that even though it's incredible in what it can do and it has inspired a lot of research and a lot of activity, it's not really open source. So it's very hard for us to use it. So at this moment, I will do another intermission, and I want to tell you a word from GPT-J. So GPT-J is a different GPT model. It's a 6 billion model. It's smaller, but still the largest open source model that has ever been released. It was released by Eleftheir AI, which is a collection of researchers whose goal is to really create and release open source models, right? And I asked a simple question to GPT-J of what do you think the future of artificial intelligence in architecture is? And as you can imagine, it said something sensible. It said is uncertain. It's going to become less about architects and more about applications that help us design spaces that do what we want them to do. And it also says that if our designs are only as good as the application, we need to start thinking about using other techniques and applications to improve our designs. So it's things that are very sensible to me. It's kind of mind-blowing that the text is really coherent, but it's also a filler text. You can imagine seeing this being written elsewhere. But there are a couple of points that I find interesting, especially the point about design being only as good as the application. In the broad discussion of, is design going away? Are we losing the essence of design with automation? It's good to remember that a lot of the essence of design is already within automation or within digital applications, right? That do a lot of the stuff that we don't really want to do. And a lot of the quality of our designs is actually tied to these tools, right? And their problems. So we need to start thinking how to make them better. And I personally think intersections with AI can help us create better applications to design. So it's not really something that's coming to replace something else, but as something that didn't exist, but really making things better, right? Improving things. So this was a word from GPT-J. So I will go back to transformers. After their popularity in language, they were also used in vision very recently, last year. And this paper on the top right, an image is worth 16 by 60 words, very nice title, introduced it. And since then, they've taken over all computer vision, right? The best generative models, they do different types of tasks. They do super resolution, they can do segmentation, they even work on 3D data, and they are, incredible quality in generation. Here on the top right, this is a generated landscape, right? And this model, we will come back to it, is called, generally people call it VQ-GAN, so it's a generative model that uses transformer architecture. And it's one of the reasons why the open source, let's say, DALL-E community has worked. But the point here is that transformers also revolutionized this field, right? And they brought, again, the lessons of scale and compute and enough data and all these scaling laws with them. Okay, so already by talking about a couple of things and just transformers, really, we've covered most of my map, right? And this shows how ubiquitous they're becoming, right? Actually, if I wanted, I could spend a bit of time and make a case that I could put in every little box and transform it, right? And there are other boxes that I will have. But we've already touched a bit of things, right? Generation of text, of structure reports, generation of scripts, which I think is something very interesting on the top left. You know, Neil talked about Q&A and design assistants. I think that's very well near into our future. And also, of course, architecture DALI and semantic generation that we will talk later. So we already touched part of my mind map. And let's see another step. So the last transformer bit is transformers in RL. This is actually very recent. This is from 2 weeks ago, I think, right? And researchers from Facebook AI and Google Brain, they came up with this amazing paper. There's been incredible research done this year. And still, I think this might be the paper of the year for me. It's called Decision Transformer, where yet again, transformers with the same idea, very simple idea of a sequence of things. In this case, is an action, a state, and a return, right? The things you do when you play a game, for example, they learn how to do reinforcement learning, right? And this is mind-blowing to me, another thing that is mind-blowing to me, because it's an incredible simple way to formulate the problem, right? And you can do it in an offline manner. So with data that you collect it somewhere. And this is perfect for architecture because almost all our data is offline. In fact, a part that I left out of my mind map is the environments of experience. We have none. I wish we had more, but we have no environments of experience to generate experience. So this is a very nice paradigm. I thought I would give a schematic for you. Imagine that you have some layouts, right? Imagine you're trying to design, you have some series of layouts. What can you do with this transformer? Where you can imagine that you run some studies on them. Let's say we run some daylight and we get a reward, right? We get our daylight autonomy on top of these models. And what you would simply do with this model is you would prefix that reward before your design. And you would ask the model, okay, this is the daylight autonomy I want. This is the design that comes out of it, right? It's that simple. It's literally that simple. You give it a reward and it gives you a design. And you can imagine that even working more and more and adding more detailing and complexity, right? For example, we can ask, okay, now I want to place some beds in my bedrooms, right? And this is the rewards I'm getting for this specific daylight autonomy based on, I don't know, comfort or getting daylight, right? And then you can ask it, okay, now I want to place my couch, right? And you can imagine this, what we are doing right now is we are formulating design into a sequence of operations. And this is really what design is about, I think. The problem is that most of these sequences are broken apart, right? Some of them happen by different people in different times, in different places, in different software. But with this kind of architecture, we can bring them together. And we can fit this into a model like that, and it could learn how to take decisions, design decisions. I think it's mind-blowing, so I wanted to really show you. I highly recommend, if you found this interesting, chase it after. I am doing it myself right now. Okay, so we talked a bit about RL, so it captures this offline RL on the top. I think decision transformers will be like huge for what we're doing. Of course, the RL, you can think about it as an assistant. Again, you can train an assistant like that because a design assistant is not really a chatbot, right? A design assistant is meant to give you solutions in a way, advices. You don't want to have a general discussion with it. So again, I believe that we could potentially train them like this. Learning through rewards, right? Learning what to respond in situations that I've seen before. And of course, robotic fabrication, online RL, all this could be tackled like this. It's an amazing paper. Okay, the last pillar that we are building on is contrastive learning. It's a very simple paradigm. The idea is you take two things that look like each other, and then you tell the model, bring those together. You take two other things that are different, you tell the model, pull them apart. That's contrastive learning in one sentence, right? Even simpler is this model that everyone tends to use nowadays, this architecture where we don't even have pairs of data. You have one data here, one image, let's say, and you say, okay, I copy this image, I give this image, the first image to one model, and then I rotate, I crop, I mix the colors of the other, and I give it to another model. And then my models learn to correlate those together, right? That's the essence and the beauty of a very simple, incredibly simple technique. The code for this is like not even a page. And it learns to do in a self-supervised manner. So it doesn't need labels. It doesn't need any work from us. It learns it has very strong representation learning, right? And a lot of the things that we're going to talk about, like Clip and DALI, are built like Clip, and other amazing models we can use in architecture, I'll build on top of this. The one that I want to highlight and extract from what's going on is this a paper called Emerging Properties in Self-Supervised Transformers, and you can call it Dino. I like the Dino name better. And what they did here is mind-blowing. And it's a really great example of what we can do in architecture, I think, with these models. They gave it images in the wild, anything, right? With no classes, no supervision, telling it, don't do anything apart from this self-supervision thing. Take the image, mess around with it a bit and learn through the image itself, right? And what it learned is it learned to segment the important parts of the image. You see here on the bottom, right? The bird, the gooses, and the elephant and the train, without asking it to segment. Better than models that we were asking them to segment. This is mind-blowing, and we go back to the bitter lesson, right? This brings together all the things that I talked about before: transformers, self-supervision, right? And the bitter lesson, because they did this with a lot of data and a lot of compute, right? And the same thing we can imagine in architecture. We generate a lot of data for which we don't have the capacity yet to label properly, or the money or the time, but it doesn't matter. We can use these self-supervised techniques to learn things. In fact, they released this model. So you can right now go download it and fine-tune it into a video drone footage you have from construction sites, right? Or maybe urban footage you have, or images of facades or material. You can do almost anything you would like with a technique like this, because it's self-supervised and with an architecture that is open sourced, right? So I wanted to highlight, I think this was really amazing. They have beautiful videos on their site if you look it up. Okay, and finally, the last contrast, and Neil mentioned this, is this big title of transferable visual models for natural language supervision. This is otherwise called CLIP. This is what Neil mentioned. I believe CLIP to be the most important open source model right now in the world. And I think it's by mistake. I don't think OpenAI, who trained it, they trained it, knew how powerful it would be or how impactful. And yet we are lucky that they released it. They released a small one, of course, but still, it's incredible. Again, it's super simple. It brings together all the things that we talked about. It has an image, it encodes it somehow into visual tokens, right? Imagine like visual words. It has words, it codes it in text tokens, and then it tries to correlate those together, right? It tries to learn to bring different modalities, and here for the first time we're talking for multimodalities, different modalities together. And it just so happens, again, with the lessons we discussed before, scaling, compute, large data sets, contrastive learning, multimodalities, and transformers architecture, and this idea, we have incredible results, right? CLIP was trained on 400 million images. That number is incredible, is insane, right? You can maybe source like a few billion images out of the web, right, if you try very hard, right? So, and for example, it can do classification better than anyone else. And it never cared about classifying anything. It just took an image and some text. There was never any supervision, right? So it's incredible. And it can do much more creative stuff. I won't show too many because I know others will show it, but I'll show a couple of things. I like to call it a trip down humanity's visual unconscious, by the way. And I think that's what it is. That's what CLIP really is. It has learned to sort of the space of the visual unconscious, or a part of it, as I said, through this. The first thing people are using it is to create art. And you can create incredible artistic results of large variety and diversity and beauty just with a text prompt. So the text that you see under these images, that was all it took, right? All it took was to prompt some models, actually CLIP and the VQGAN model we mentioned earlier, and create some beautiful images. I think this is mind-blowing. And the AI art community that is developing more and more by the day because of this has been doing amazing stuff with this thing, right? So this is one application. I tried to do something similar very early on. This is not very nice, but I wanted to show because it's a bit architecture related. It was a style gun trained on buildings. It was mildly trained, very small data set. No, I didn't have the computer or anything to do it, but still you can see that it understands what you want it to do, right? For a small house, it has this top-down view almost of a small house. A large office tower creates a large office tower with some background. And even this, two buildings next to each other in front of a park creates the scene of the image. It's not, of course, something that you would use direct in a presentation, but it gets you halfway there, right? This is the idea of this tool, ideation, right? To create creativity, and I think they are very good for creativity. The other thing that I try to do is I try to understand how well it understands semantics, and it actually does. I gave it a prompt about, buildings around the square, and then I put cloudy, rainy, snowy, or sunny day, and it actually changes the effect of the image accordingly. If I could zoom here, you can see the water on the ground. it's mind-blowing that I can see the water on the ground on a rainy day. So you can see that we're already at the point of, we are not at artificial intelligence. Okay, I don't want to hype anything out. We are not there, it's not there, but we are taking steps on something more intelligent by simply having more modalities together, right? And also we are taking steps at more practical things, and that's what I want to show you after. So the question I ask myself is semantics all we need, right? Can we just do a lot of things that we cannot do before? Like all this was impossible just by adding semantic information into our data sets, right? And this is what I try to answer with my work that I will present now very quickly. But before I do that, I will take a small detour from Picasso to talk about representation. A lot of things about we discussed and I discussed are about representation. And the only way I can show it through art is this image from the bull from Picasso. I'm not a very artistic person, but I know how to understand this. So Picasso spent most of his life understanding representation. That's his work, essentially, to dial down to what is really the essence of representation of a bull here, right? And you can see how complexity reduces and it becomes more schematic and abstract. And I really love the fact that at the end, on the bottom right corner, he has his signature, because in a way, it's a signal, he didn't mean that, but it's a signal for me of this multimodality, right? That of course we can find ways through architecture, data, and like just scale to find very good representation capacity, like the schematics of Picasso, but maybe perhaps also this semantic, this language that we can add at the end can really bring us on top. And I think this is a beautiful scheme to understand what these models are trying to do. They take a complex image and they try to dial it down into something less complex, but having the essence, let's say, of what the thing is. And I think if Picasso was alive today, he would love AI and would probably create networks of his own. So, okay, semantic generation. I think this is a new frontier of design, right? This is what I want to talk to you mostly about, and this is my work. And what I mean about frontier is very literal, right? The extreme limit of understanding in a particular area. I don't mean this as new tools that we can use to design what we did before. None of that. If we do that, or if I do that, it's going to be something weak and you can call me out, right? What I mean is that through this multimodality, and this semantic modality can be more, right? We can add more multimodalities. We might get a glimpse into areas of design or understanding of design that we never had before, I think. And also, what is very important for me and my work, maybe everyone can do that. Why? Because we are just using semantics, right? We're not using code, and we're not using deep learning and AI. We're not using Grasshopper and Rhino, things that people don't know, never had the chance to know perhaps, or maybe they don't have access to. We are using language, right? And intuition. So these tools, if we can make them work, they will expand the limit of understanding for what we're doing, both because they will allow us to do amazing things, but also importantly, because they will allow people that would never have the chance to do design to design, right? So this is my vision. Now we are dead on the architectural DALI and an architectural clip, right? And all the semantic annotation and generation, and this is kind of my work. So Neil showed this, so I won't go too much into it. So this is DALI, right? OpenAI model released. The blog was released last year. The model was never released, of course, and there is no API yet for it. And it created this amazing, avocado chairs and, like autocomplete cards, but it was never available to any of us. Thankfully, a large open source community, of which I'm part of, a small part of, replicated the code and have created an open source code, right? And on top of that, I started working and struggling to see if I can do something similar, but not exactly the same, for architecture, right? And I started with layouts, right? This is what I call an architecture DALI. So I started by seeing if we can semantically generate house layouts, a very simple thing that we do every day. How did I do this? Very simply, I created the data set. Here you can see the 6 different, let's say, typologies of layouts. I measure them with different numbers of bedrooms and bathrooms. Bedrooms are green, bathrooms are pink, right? For some reason, this is a toy experiment in many ways, right? And then on the bottom, you can see that for a specific apartment, I have semantic annotations. I create myself. This is what I mean by the new ways of data generation, right? And those are about what type of rooms we have and how many rooms in total, what adjacencies do you see here, and what locations do you have of the rooms. You can imagine this list being as long as you like it, right? You can put textures and renders and images, whatever you want. I started simply, but you can expand this. That's the whole point of semantic generation. And then, of course, I needed scale and compute. So the model is around 1 billion parameters. So it's a small model compared to DALL-E, but it's quite large. You need like a couple of good GPUs to train it. And the dataset is around 400,000 layouts. So it's kind of, it's getting there, let's say, on the scale. And so you can see that, in order to get results, you still need some of the bitter lesson, right? So it's not like I can do this with 3,000 layouts and some annotations and it works. And actually I did that with 3,000 layouts and the results were very ugly, I would say, but still very promising back then and led me to keep working on it, right? So let's see what happens. So this is the first thing. So what happens here? We have about 35 designs, and I'm sorry, I should have done less. 35 layouts, right? And how were these layouts generated? Very simply, by giving a prompt to the model. I typed a house with 3 bedrooms, 2 bathrooms, and a corridor. And this came out, right? When I first saw this, I was very nervous, right? Because I was training this model for a while. What's going on? I don't know what will happen. So when I first saw this, I was utterly mind blown, right? Because I had literally created things that look like layouts, and I did it with a text prompt, right? Of course, I had done a lot of work before and training the model, but the user of that model just did it with a text prompt. So I was really mind blown. And I really, at that moment, and also when I saw the clip art before, those 2 moments were the ones that made me really, truly believe in this as an next frontier, right? So let's see a few other examples. We will see a few layouts here, but I want to show you the capabilities, right? So here I asked it for a house with 7 rooms and a corridor, a bit more open-ended, right? And this is how you can add open-ended generation, another advantage of semantic generation, something that is very difficult to hard code if you do it yourself. So here I just asked for a number of rooms. So the model built 3-bedroom apartments with 1 bathroom or 2-bedroom apartments with 2 bathrooms. Why? Because they have 7 rooms altogether. So it learned how to generate through this prompt across different typologies, right? And of course it learned because it was in the data, right? But that's good. That's what we want. We want the model to learn to generate what we are trying to teach it, right? Another idea was, can I generate by location, right? So here I prompt the model by a bedroom is located in the north side of the house. You can imagine the orientation to be the compass. So the north side is the top. So what happens here is very simple. I ask for a bedroom, just one of the bedrooms, to be located on the top, right? You can see all of these images. They have a bedroom on the top. Of course, the model very correctly built many different apartments with many different numbers of bedrooms, right? Why? Because I never said how many. I just said one of the bedrooms has to be on the north. Again, it's learned to sort of semantically generate things that are more refined than you would expect, than that I would initially expect are possible. Of course, this is possible because it was in the data. And this shows, again, the possibility of the semantics that you can keep adding to the model, right? So let's see what happens if we ask it for the bedroom to be located in the north of the side of the house. What happens then? Well, very correctly, at least in this prompt that were the correct ones, the model creates a 1-bedroom apartment that has a bedroom on the top of the image. Why? Because I said the bedroom, the unique bedroom, to be located in the north side of the house. Again, the model was able to catch on this and create. These are the successful, let's say, prompts. Every time the model, I should say, it generates 128 in my experiments. But even the failed prompts of this, they were still 1-bedroom apartments. It was just the location that had failed. So I was very, very, very satisfied by that. So let's see something else. Here, I'm asking you to, again, okay, this one we won't stay too long. Here, I talk about bathrooms in the northeast, so top right, it does it. And again, the bathroom in the north side, again, it does it 1 bathroom, right? And again, we see that it has 1 bathroom and 1 bedroom in some cases here, 1 bathroom and 2-bedroom layouts, 1 bathroom and 3-bedroom layouts, and all this stuff, right? So it generates across typologies again. And all this that we've seen so far is just text, right? So if this model is released, and I hope to release it with a public web API for people to experiment, all you will have to do is log in the site and just type your text, right? And it will generate some layouts for you. Then we can generate it with adjacencies, right? Not everything's successful here. I on purpose put the things that failed because those are on me and not on the model. Here you can see like a white space, the corridor is missing. I forgot to print it out. So I wanted to call out my failures, but also like it's important to look through your failures in a way, through the mistakes, and look at the beauty of these things. So we ask it for adjacency between kitchen, this sort of very bad colors I chose again, this sort of, I don't know, not really dark pink, I guess. And the living room, this is sort of dark gray. So you can see it tries to make them adjacent. So at least to touch, even touch a little, right? And then when I ask not adjacent, it creates apartments that are not adjacent, that have the kitchen somewhere else. So you see here, the kitchen is far away from the living room, again, is far away. And it finds some interesting ways. For example, here in the center, it found a very interesting way of satisfying the prompt by not having a kitchen in the apartment. So that also was nice because this is completely out of distribution. All the inputs it saw had a kitchen. But here the model is sort of decided not to give a kitchen, which is a solution to this problem. And I really like that, actually. So you can see it finds like, and the amazing thing is that, again, the layouts differ because we're not asking you for a layout. We're just asking you, just give me an apartment of any type that has this non-adjacency. And there is also quite a bit of diversity of design, and that's what I like as well. Even though some of them are not very realistic, if you'd say, that's on me again. I generated 400,000, some of them are going to be a bit boring, right? But it's incredible to me that the model is doing this right now. Now, what is interesting to view is also out of distribution, right? So if you remember, I had some typologies, but I never had a typology with one bedroom and two bathrooms. I don't know why, don't ask me, I forgot, or I was tired of generating, but I never had. So what happens if I ask of the model of something that it never saw out of distribution, right? Well, it tries to generate. It doesn't generate as many successful as before. So this is the 8 best that I got, right? But it still is amazing to me that it's generating even this 8. And you can see some of them are quite clear layouts, with 1 bedroom, which is the green, and 2 bathrooms, right? And, this one makes sense. I don't know. I think it makes sense. It has a bathroom in the bedroom and then another in the living room, right? So this is a robustness test in a way, right? Can you generate things that you never saw? And the model is actually trying to do that. And I think, this is my intuition, that this will become better and probably completely solved with scale when we go from 400,000 to 40 million images, right? Again, here I ask it for 3 bedrooms and 3 bathrooms. Again, never seen before, and it creates some nice layouts of 3 bedrooms and 3 bathrooms. And again, I do the same with 2 bedrooms and 2 bathrooms. Don't ask me why I didn't have that, but I didn't. And then it generates something. So it actually can do it. It's not just overfitting to the annotations we gave it, right? Because that could be the issue. And there is a bit of overfitting perhaps already because of the size of the model, but it could be the issue that it's just learning to memorize, right? But these things it never saw. So it has a potential for generalization, and that's incredibly important for us, right? Because we want it to generate new things, right? And again, 1 bedroom, 2 bathrooms, and you can see, this one is not correct actually, but you can see it generates some of them here that are kind of realistic. So it works out of distribution. Again, to me, it's totally mind-blowing. So I will go back. I want to go back to the decision transformer, and I'm almost done here. I want to piece some things together. Already, the semantic generation, I should say, it brought almost everything I talked about before, right? Together. It brought obviously transformers. It brought multimodality. It has brought the scale and compute, because to create actually robust and models that can generalize across designs, you need the scale, and you need much more scale than I already have. It's brought together, even the contrastive learning, because at the end we will need to rank these designs somehow, and we will do that with these contrastive models. And I think we can now sort of see the image, how it all comes together. And especially I saw the full image, I think, when I saw decision transformer, right? So remember what we said before. In the decision transformer, we have a sequence of operations that is literally us designing something, right? And at one point, we need to have a layout. So what if this layout was made by DALL-E, right? What if you had that sequence of operation was a semantic annotation, right? And what if at that semantic annotation, you could also say a high daylight autonomy apartment, right? So you can prefix something like that. And then, of course, to do that, you would need to actually simulate things, right? All these rewards that I have here, you have to simulate. That's quite cost consuming in architecture and a big problem for scaling things up. So what if we had surrogate models like infrared? Neil talked about infrared, which is our model that predicts performance in real time across metrics. Infrared is just an example here, but just think of them as surrogate models. So what if you can train surrogate models to predict all these, rewards, right? And this comes together now. You can see how it comes together as a sort of coherent way of intelligent design in a way, right? And you have a lot of things that are not possible before here. You have the real-time performance. You have this stepwise approach, right, of training a model that can take one decision after the other. And you have a semantic generation that not only allows people with not a lot of knowledge in, coding or anything to generate things, but it also allows them, this is the most important, I can't stress enough, the embedding of constraints in design generation. It's incredibly difficult. Anyone who's done computational design will tell you how difficult it is to hard code all this stuff, to hard code constraints and, I don't want this, and maybe minimize this and maximize this. None of that you need it because it's all in your semantics, right? You can embed your constraints in your semantics. So this is my full image, and maybe semantics is all you need. Maybe that's where we are now. And I really think, and I hope that I can prove this very soon, right? And one last thing that I want to tell you is that a few months ago, I made this chart of a lot of boxes where I was trying to understand what system I want to build, right? Even before I knew about semantic generation. And a lot of these things I've done before, like this prophet is about predicting performance. Okay, I do it in my work. Evaluation we've done, some generation we've all done if we did the grasshopper computational design. But the hardest part I realized was the part on the left side. Why? Because this part's on the left side, initiating the design and coding constraints, is where the humans, us, mostly take part in, right? And it's really, really hard to sort of code these things, to code human preferences, right? Why? Because those change. We have millions or billions or infinite of them, right? So it's really hard to hard code things. It was a problem that traditional AI in the 60s had when they were making expert systems, right? They had a bottleneck. Like every time a new knowledge came, they had to rearrange everything. So what if all this part that is very human-based, right? We can still keep it human-based, but sort of abstract it with this semantic generation. This is sort of where I see the future, right? Where I see the frontier. We still need evaluation. We still need to learn. It's very important to start learning out of all this data. And in my chart, I will tell you in a second where that is. And, maybe have a critique on top of it and then visualize, which is the ASOP here. I'm using the ancient Greek stuff. But semantic generation, I hope, can abstract all these very, very, very difficult decisions and, engineering we have to do in this model. And going back to my map again, I want to say that, this map is very narrow, right? It's narrow. Why? Because it reflects my interests. And even in that, I didn't have the time to populate or discuss about everything. But that's not the point. The point is that I think, right, and I'm going to be very poetic here, I think that all of us have a map like this inside of us, right? We all do. And you should not be afraid of charting a map like this because there's nothing to be afraid of. Like, in my opinion, and I've said this in many places, and I will keep saying it as many times as I can, we have as much to offer to artificial intelligence research as AI research has to offer to us, right? And this, if anything, is my message today. Let it be this, that you shouldn't be afraid, just venture into these ideas. And thank you very much.
Theodorus, that was fantastic. Just before we move on, I just want to put, there's a question here in the chat from Miriam Maya, who I think is in Brazil. And her question is about the adjustment of rooms. Did you use the bin packing meta heuristic to calibrate the algorithm? Did you use Galapagos? Ask him because I'm studying about it, and remember me when I made tests with friends and we have some simple results. Yeah.
Hi, yeah, thanks for the question. We can talk implementation, I guess, also later, but no, this was, you don't need anything like that because you're not optimizing anything. You just want to generate a variety and diversity of data, and then you just use that data to learn, to teach a model that can then do all these things. So you're trying to avoid this optimization. And so these were created with no a metric in mind, and with a tool that you can find is open source. It's called magnetizing floors, and it just creates, let's say, a variety of floor plans. So it's really a toy experiment, but still you can see how amazing it works, I think.
So, okay, that was great, Theodorus. I mean, a lot of very provocative questions there, and I will save my questions for the end. But I think it was, remarkable stuff and very, very provocative. I particularly like the humanities visual unconscious. That just blew my mind. That's a fantastic concept. We've got two presentations. I'm really was kind of keen to bring in the younger generation. So those who I think are destined for doctoral research, but not quite doing that yet, just to show some of their work. And I know that we've got some very good people in the audience as well, so I want to leave some time for questions at the end. So I want to invite Matthias, first of all, who is Matthias Tancati, who is literally just graduated from his master's. He's from Brazil, and he was responsible for the TikTok one message, if you have seen it at all. Matthias, would you like to share your screen?
Yes, of course. Hello, everyone. Just give me 1 second. All right. So first, thank you very much for inviting me to be in this amazing stage that is Digital Futures. It's a pleasure to be here. And before I start showing my exploration with Clip and AI, I just would like to say that usually when we talk about AI in architecture, there's a lot of conversation about replacing the role of the architect with artificial intelligence. And I just want to say that there's also the potential that this is going to be expanding the toolkit that architects use in the creative process to create buildings, to create spaces. And this is something that I believe. I also share a lot of the things that Theodorus was talking about. And it's this idea of expanding the tool set. Even if you want to go deep in it, we can talk, have a whole lecture about it. The whole thing that Andy Clark and David Chalmers talk about, the parity principle, the idea that you can do something outside of the brain that if done inside of the brain would be considered cognition, could be then considered part of our cognitive process. So this idea of expanding what our brains are capable of doing with outside resources, that's where I think the interesting thing with AI in architecture is coming. So moving on, my introduction to AI, how I started exploring with it, was actually during my thesis project earlier this year, which I presented in April. And my project was about modifying or augmenting our perception of an architectural space using memories and biometric data, actually data from your own body. And to simplify this project as a whole, once you have a version of the physical space digitalized, you have a digital copy of the space, and you can align it to the physical world, you can then modify this digital space to then change how you perceive it, still being able to access as a whole. And how I actually brought this idea of memory and capturing a memory using AI is the idea that if I have a scene, meaning your childhood home or a wedding that is very remarkable for you, or the circumstantial space where a memory is formed, you can then use an image to text algorithm to then recognize or give you a text description of what it thinks the space is. And then I use that text data, that semantics, as the input for then creating images that do not exist, and then using Clip to generate versions of that description that are then generated. So in my case, using, for example, a chest band or an Apple Watch, I can then track my heart rate variability, which determines, the distance between each heartbeat, which, papers have explained before how you can actually tell if you're being, the difference between being frustrated or appreciative. And if that is associated with the actual space around you, how can you then take images from this space, this one episodic memory, and then translate it into language, text, probably a building covered in plants, probably a greenhouse, and then from that text generate thousands of variations of that space using Clip. So here what we can see, using that space, now I can then combine it with the images of the room, the space that I'm trying to augment perception, and then create the building blocks, these different pieces of this merge between the two to then create this augmented space using the memory from a moment when I was happy or sad or frustrated to then modify the circumstances or the context in which I'm experiencing now. But even though there was a prototype for a project, the interesting thing is how we can generate all of these different rooms, images of spaces that do not exist based on language, which Theodorus explained beautifully. I'm not going to get too much into the actual architecture of that. But I think this is the power that is going to come with architecture. Even though these rooms might not be 100%, realistic or photorealistic, you can still get a sense of what the space entails based on the prompt And in this case, the prompt is a building covered in plants or a building covered in ivy. And you can see here, for example, that even though it's not photorealistic, you can distinguish and perceive what is a window frame, what is the plants invading the room, the texture on the walls. And that is what I believe the power of this relies. And what I think the most interesting thing that it could be applied to right now at the stage that it is actually architectural research. I've been looking at neuroscience and the actual implications of neuroscience in architecture. And one thing that I want to bring attention to is this one research paper done in 2017, and it was a collaboration with Iran University of Science and Technology, University of Tehran, Berlin Institute of Technology, University of California, and University of Technology in Sydney. And what they were studying is actually creating this controlled environment to be experienced through VR, and then using EEG to actually measure the actual brain activity in different architectural spaces. So you can see they actually model different versions of architectural spaces with different conditions of roofing, height, perspective, and then measure the actual response from human body. And by doing that, they can actually track the specific distances from the wall and specific conditions that have a general response on the human brain. And what I think is interesting to think about AI in these circumstances is the possibility of creating any space based on language and thousands of variations of it. This is, for example, one collection of images that I created for my research, and the prompt is a room full of plants. And then it generated all of these variations of what a room full of plants could have been, even though there's no modeling and no actual design. It's just based on this text prompt. And another example is all of these buildings made of gold, made from the same prompt. And you can distinguish what is a window, what is a door, what is the actual, condition of this building made of gold, even though none of it really exists. And the most interesting thing about this is that one image can actually, be generated so fast, and you have a whole collection of images. And necessarily what you're generating is not what is, what it exists, in the sense that this, for example, is a clustered room full of books. And the idea is to generate thousands of tight spaces full of books everywhere. And most of them actually don't even look like a space or a room, but then you can find little spaces like this on the corner that are actually hinting what a space like that would be. Or then examples like this. The prompt is a brain building, a building made of brain. And then each generation, it goes refining itself and generating what this specific seed or this variation of the prompt would think that a building made of brains actually would be. And another example, this one tent system that is made of mosquitoes. So, understanding what makes a mosquito, understanding what makes a tent, and then morphing those together. If you want to talk about the whole idea of biophilia and architecture and design, actually, the structure of what makes a mosquito stand up versus the structure that makes, a tent hold itself together, and then morphing each other as perhaps a creativity tool, a tool that helps us think of things that we wouldn't think before, but definitely a strong tool that we're going to be seeing more and more in architectural practices. Thank you very much.
Thank you, Mr. That was amazing. You've really been producing some fantastic new work. When I see this, I can see this younger generation absolutely kind of getting stuck into this, and I just, what's going to happen in a few years' time, I don't know. But that's fabulous. I some wonderfully suggestive images as well. And I'm left thinking about how does memory really come part in it, and how do we really understand how the role of memory, almost like in terms of what we generate comes out of our memory, and in the same way as that what comes out of the what the output is comes out of the input. So if in computation, there's something that's super interesting there. Let's move on to Maya, because I want to try and save some time for the end. Maya, I don't know if you can do a slightly longer. You have two versions, slightly longer version. I want to save a little bit of time for questions at the end. Yeah. Do you, Maya?
No problem. Can you hear me well?
Yeah. So just say that Maya's also just finished his master's at the University of Illinois Champaign. He has been incredibly prolific in terms of posting material from videos and interviews and so on. And I think last year he was somebody whose life was transformed by digital futures, and suddenly, and I can see. I mean, one of the things my role is to pick up on talent, and I can see that Maya has got a big history, got a big future ahead of him. So Maya, over to you.
Awesome. You just said a line which I wanted to cover in my intro, that like for people who are watching this for the first time and are hearing AI in architecture, like I was in your shoes a year ago, and if you finish this whole lecture series, you are way ahead than like I was last year. So this is an amazing movement and initiative, and I am fortunate and grateful for this opportunity to present. So yeah, I'm a AI technology activist, and I'm currently an applications developer at Perkins & Will, and I create content on engineer architecture. So you can see all this visual in way higher quality if you go to my channel. The image, the GIF in the left is a prompt I gave of New York Central Park, how it will look like in 2050. And this is just a compilation of it. So I would like to say, start with what are the trends in software architecture. So software 1.0 is rule-based programming, where you design the algorithm, and similar translation in architecture is your parametric design scripts in Grasshopper, Dynamo. Software 2.0 is data-driven programming. So you curate the data set and you can integrate those ML algorithms in your design, as we saw. And software 3.0 is prompt engineering. And you heard a lot in Theo's presentation, in Matthias' presentation, how they're working with the prompts to curate their data. And GPT-3, Clip, plus VQGAN are some of the ways when curating the design prompt. And I would like to have a modified version of Cedric Price question, that AI is the answer, but what are the prompts you are giving? I think that would be more important from now. So if someone has asked me question, can AI generate realistic images just from few words? And like that question, if you just reflect upon it, it's very difficult. Like it's next to impossible thing. But in my explorations, you will see how Clip, along with other generative models, are able to generate very realistic images. So hold your seats tight. You're gonna get an amazing ride of Clip generated designs. So as it was mentioned earlier, DALL-E is text to image AI model. Clip is connecting images with text. So in a simple manner, if you have a text and if you have a list of images, it will able to find the best match for it. Similarly, if you have an image, it will be able to find what is the most similar matching images. And also this transformer, it started with natural language processing, and now it's also being used for vision tasks, and it's able to generate very detailed images. So I would like to share a few examples where with my prompt question and what kind of image it was able to generate. So there's like parametric building design, compare consists of 3 museum design, and I added like prefix of Zaha Hadid, and it has some element of it. And also I wanted to test out, like, can it generate construction drawings, or can it generate napkin sketch? So as you can see, it's able to generate like napkin sketch by Frank Gehry. High performance building, what does a novel architecture building in 2050 look like? A happy social urban space, where it's able to have like those characteristics in abstract manner, and like one could get a lot of design cues out of it. Also, I really like this of abstract architectural design for museum, conceptual pencil sketch for museum design. And these are way more realistic, and I was awed by initially when this drawings artwork was produced. then I started, okay, we have the static thing. And I am also in AI art Discord group, which Theo mentions. And they were generating this zoom animation. And I thought, wait, can we translate this image into an animation of walkthrough? And initially when they had like rotation and zoom feature, I experimented with few variables in the generative network, and I was able to produce shear or a panning mode in those model architecture. And just to clarify for those who are hearing model architecture, a lot of terms in software and architecture are similar. So model architecture is basically like the neural network, how it's defined, and that's what is model architecture in case you're not clear. So as you can see in the first GF, it's a walkthrough through a art gallery designed by my prompt. Second is a hyper-realistic Unreal Engine brutalist architecture, and I added also pre-prompt of Tadawando, De Corbusier, Louis Kahn. And once you start experimenting with these clip models, you'll start realizing what are some keywords or prompts which produce way more better image. So in the community, AI community, like it's a lot of people after their experiment, they know that hyper-realistic, Unreal Engine rendered are some keywords which are producing way more better output. Also in the right, you can see how a Tokyo nightscape with neon lights. Also like neon lights, when I added in few of my exploration, it created a really aesthetic look in the output. All right, so these are many more variations of my prompt for how would an art gallery look like. So as you can see in the top, I added a prompt of cyberpunk city with artwork by Rafik Anadol, and it has very minor aspect of it, but I was impressed. Then this second one is classical architecture with neon lights. So if you look at the ceiling, it has element of that. The third one is about art gallery, modern art gallery in which might have been designed by Frank Gehry. And there is this sculpture which kinds of give away the style. And the one below is I had Zaha Hadid in the prompt instead of Frank Gehry. In the right, so few of these are panning from right to left. This one is going zoom. So there are a lot of variables you can play with. Then I thought, how would a futuristic museum designed by Zaha Hadid look like? And I gave a pre-prompt of Zaha Hadid and Kazimir Malevich, like whose artwork also is inspired by. And if you look at this animation, like on each instances, you'll find people sculpt like some aspect of Zaha's form are being translated into the output. And below are some variations of clip with other generative network. So this the ones which I showed earlier are clip plus VQ GAN, but also you can combine clip with any style GAN, big GAN, or also clip with DALI. And the ones below, I was so surprised when I said like parametric design by Zaha Hadid, and it was able to generate Zaha's faces in the output. That was quite surprising. And even like this one has some character of museum in its. So it was quite interesting exploration. Few things this is being discussed like in the morning that a very famous AI artist and researcher Daniel Russ has developed a script where earlier we saw clip was able to generate images, but what if clip has been also correlated with the mesh, and so clip to mesh. So here the prompt is make a mesh as monkey mesh, and you can see the transformation, and also like architecturally like mesh sometimes has a more like end use case. So it's another thing. I think with time we'll see more and more explorations with clip on the mesh object type as well. And one thing I realized from my experimentation is like if you just treat the collab script and just play, it is a black box. But once you read research papers, understand what each different part of the code does, it will provide you much more flexibility for experimentation in your design. And like, as I said earlier, that I wanted a pan mode and walkthrough mode in my clip navigation. So when I'm experimenting with other parameters, I also played with the shear of the image. And you can see many times the model failed, but it was a part of the learning process where how you figure out how different parameters can end up lead to different output and also different prompts. So don't be afraid to experiment always. There are a lot of good blog posts and YouTube tutorials on how this model works. So, Neil, I don't know if we have time for 2 minutes more.
How long is it? Can you do
2 minutes?
2 minutes? Yeah. Okay, go ahead.
Okay. Yeah. So one thing I want to clarify, we see a lot of visual AI related work in architecture, like in terms of style GAN, other GAN based, but there is a whole another spectrum of other like graph based neural network or reinforcement learning, which has some interesting applications in AI research. So I'll just give you a one line summary. So this is quite interesting paper by Housgen where they take input of bubble diagram and produce generative house layout as output. And they just recently released Housegen++, which has more functionality of interior doors. Another good paper is Sketch to optimization. So it takes sketches, makes a BIM model out of it, and then you can perform multi-objective optimization. Plan to Scene, it was just released yesterday where you could take a floor plan and make a 3D model out of it. And also it's also coupled with images in the floor plans, and a lot of defects in terms of lighting has been eradicated within the model architecture. 3D scene graph is like another very interesting area of research where you can do scanning of the building and it will able to generate BIM model out of it. And with LiDAR being integrated in new iPad, and it's gonna make image to 3D model way more easier as we move on. And this is another interesting paper, Intelligent Home 3D, where just based on this linguistic description of one living room of this texture, it's able to generate 3D house layout out on based on it. So I always wondered, since a lot of these developments are going on, like what are we being trained or be aware of what skills would be needed in future? And I'm still looking for the answer. But one thing based on my research, it looks like quick 3D modeling and rendering might be less needed skills in future. This is again a controversial thing, but this image is based on last NVIDIA's conference. There's a company who are combining VR plus ML content creation. It showed that an experienced artist with 5+ years of experience took 10 hours to create this 3D model, but with the help of AI, without any 3D modeling experience, it was able to generate in 45 minutes. So that gives some kind of hint that where should we invest our time and what kind of problem solving should we do. So a few things which came on top of my mind was like, as a AI architecture dataset curator, where we do like more feature engineering problems, specific data processing, customization, AI design technologist, where we integrate different algorithms and models in our workflow, prompt engineering, as we saw how different prompts were able to produce different graphics, and also like Open AI GPT-3, I experimented with the beta version. It has a whole new way we can find design cues for precedent study or site analysis. It gives a lot of insight, but it depends how you understand the prompt. So yeah, that's it. Thank you.
Yeah, that was great. That was great. I now realize I should have left more time for your presentations, and actually maybe I should have ramped things up a bit more. I gave a kind of introductory level thing, but it seems like the level has already been ratcheted up. I think that I wanted to thank Theodorus for setting the tone there, and really, that was a fabulous presentation. Also, I mean, Matthias and Mayo for, I think what I get there is, what I continually get from your generation is this kind of excitement about the possibilities of what this is opening up, and you guys are the future. So thank you so much for all this thing. we're gonna have we have to wrap up in 1 minute's time. Hopefully, I'll leave more time for questions tomorrow. And I can see there's some very talented people in the chat there. But I just want to maybe invite Philip Yan. I don't know if you'd like to say something at the final end. Philip has been part of trying to set up this platform together. Whether you'd like to kind of reflect on today's presentations, Philip. I don't know if I don't want to put you on the spot, as it were, but would you like to say something? Okay, maybe Philip's not there, but tomorrow we'll have Daniel Bolojan talking about GANs themselves, and I guess many of you, I never quite know what background you've got. Maybe some of you have already been experimenting with that anyway, but we'll go through that. We'll also have Lev Manovich, who is a really quite a central figure within the area of media arts, looking at the whole question. So I think tomorrow's going to be a very exciting day, and today was as well. I'm still blown away by this, and I think my experience of these platforms where you bring everyone together, it becomes like a brain, because the interaction across the globe is just unbelievable and so immediate. So thank you so much. Thank you, Theodore in Kuala Lumpur. Thank you, Maya in, I don't know if you're in Illinois or wherever. And thank you, Matthias. It was fabulous. And we look forward to building upon that. So this has been a fabulous first session. We've got 5 more to go. I'm going to take more of a background in the future and allow more of you guys to go and present your work. So thank you so much, everybody. Do we have any final comments? Okay, all right. So tomorrow, I would just say tomorrow morning, well, okay, not say tomorrow morning, but in China it'll be the same time. But at 10 o'clock in the evening, China time, at 10 o'clock in the morning, East Coast time, at 4 o'clock in Central European time, we will have a lecture as part of the Architecture and Philosophy group. It'll be from Sanford Quinter. Sanford is an astonishing guy. He's absolutely astonishing. Finally, one final comment, since everyone is here, can I simply say that we still don't have anybody who has submitted, who are workshop instructors who've actually submitted their selection of students. We need that as soon as possible. And I want to just thank some of the people in this group today. Theodorus and Maya and Matthias are all contributing to the workshop, which is a wonderful gesture. So thank you, guys. That was fantastic. Thank you.
Thank you. Thank you for organizing.
Oh, thank you for being part of it.